We will now study vector fields. So this image here shows the gravitational force exerted by the Earth, so by Earth and by Luna, which is our moon. Right, so this is the Earth here, this is Luna, and this is the gravitational force. At any point in the field, the vector associated with it gives the net gravitational force exerted by the two objects on an object of unit mass. So no matter where you are in here, the vector is going to give you the force that that object's going to experience. So if we're here, right, we're going to experience a force there, right? So as you notice, the closer you get to the Earth, it looks like the stronger the gravitational force, right? Same thing with, of course, the moon. The moon's gravity is going to be outdone by Earth's gravity. This image shows the velocity of water particles on the surface of a river. The vector associated with a given point on the river surface gives the velocity of the water at that point. So again, you can see here, very fast velocity, up here, not so much. Now, of course, these are not the only situations in which such a phenomenon occurs, so we would need a way to describe such phenomena. A vector field f in R3 is an assignment of a three-dimensional vector f of xyz to each point xyz of a set D, which is a subset of R3 space. So the set D is called the domain of the vector field, and informally, a vector field is a multivariate vector value function. So here we have the graph of the vector field x over 2, y over 2. And over here, it's the same vector field, except now it's superimposed with several circles. Right now, you can see then that the vector field, it's radiating, right? It's radiating away from the origin, at least for this one. There's another property. Notice all of the vectors are perpendicular to the circle, right? So this type of vector field is what we call a radial field. So these types of fields model certain gravitational fields as well as energy source fields. In a radial field, all the vectors either point directly toward or directly away from the origin. Furthermore, the magnitude of the vector depends only on the distance it is from the origin. In a radial field, the vector at the point xy is perpendicular to the circle centered at the origin that contains the point xy. Here we have another example of a vector field. This is the vector field y negative x, and again, superimposed with circles. Now, this one, look, the vectors seem to be circling the origin, right? So this type of vector field is called a rotational field. These types of fields model the movement of a fluid in a vertex, or a vortex rather. In a rotational field, all the vectors point either in a clockwise or counterclockwise direction, and the magnitude of the vector depends only on its distance from the origin. Now, let's suppose that this vector field right here is the velocity field of a fluid. We're asked to determine how fast the fluid is moving at the point 1, negative 1, and assume the units of speed are meters per second. So essentially what we're looking for is we're looking for the magnitude of v evaluated at 1, negative 1. So there are two ways we can go about doing this. We can go ahead and calculate the magnitude of v of xy straight up, and then plug in 1, negative 1, or, and in my opinion, a much simpler way, is to first calculate v of 1, negative 1. Alright, so doing this, we'll get negative negative 2 over 2, comma, 2 over 2. So we just get the vector 1, 1. Now we can just take the magnitude of this, and we get the square root of 2. And the units are meters per second. So evaluating a vector field is the same as you would evaluate a vector valued function. Right? You just plug in the points, except now it's multivariate. So it's a combination of the multivariate functions we studied previously and just before that the vector valued functions. A vector field f is called a unit vector field if the magnitude of each vector in the field is 1. That is, if every vector in the field is a unit vector. In a unit vector field, the only pertinent information is the direction of each vector. So it acts more like a direction field. So we're going to show that this vector field here is a unit vector field. So what we do is just calculate the magnitude of f of xy and show that this is 1 regardless of our choices of x and y. So this will give us the square root of y squared over x squared plus y squared plus x squared over x squared plus y squared. Now they have the same denominator, so we can add them together. Y squared plus x squared over x squared plus y squared. So this is 1, square root of 1, which is of course just 1. Now notice that this does not depend on our choices of x and y. So we can conclude that f is a unit vector field. Now recall that we studied the gradient, and in doing so, we looked at a new operator called the del operator, and it was defined as partial partial x, comma, partial partial y, comma, partial partial z. So it was a vector operator. Right? And recall that the gradient was del f. Now, this kind of looks like scalar multiplication, right? Where nabla is the vector, f is our scalar. Well, there are two other type of vector products we looked at, the dot product and the cross product. Well, we can actually use these two products along with nabla, the del operator, to get new operations. The first one is known as divergence. So if f is a vector field, then the divergence of f is defined as del dot f. The divergence is an operation that tells us how the vector field behaves toward or away from a point. Locally, you can think of the divergence at a point P as a measure of the outflowingness of a vector field at P. So for example, if f represents the velocity of a fluid, then del dot f of P measures the net rate of change with respect to time of the amount of fluid flowing away from P. Now we will delve more into the interpretation of divergence when we study the divergence theorem at the end of this course. In fact, the divergence theorem should be, at least how I have it laid out right now, the very last video in this series. So let's go ahead and find the divergence of our vector field e to the x, y, z, negative y squared at the point 0, 2, minus 1. So the first thing I do is calculate del dot f. So remember, this is partial partial x, partial partial y, partial partial z. Then it'll be dotted with e to the x, yz, and then negative y squared. Now, while this is technically an operator, we can still think of multiplication, except it's now multiplication where the order does matter. So the dot product says it's going to be the sum of the products of the corresponding components. So it'll be partial x of e to the x plus partial y times yz, or of yz I should say, not times, and then partial z of negative y squared. Okay, so partial x is e to the x. Partial y of yz is just z. And then partial z of negative y squared is 0. So we're left with e to the x plus z. Now we just plug in 0 to negative 1. So del dot f of 0 to negative 1. We get e to the 0 minus 1, which is 1 minus 1, and so this is a divergence of 0. The second operation is known as the curl. If f is a vector field, the curl of f is defined as del cross f, which is, of course, this vector here. Partial r, partial y, I'll let you read through that. Now, curl is an operation that measures the extent of rotation of the vector field about a point. So, for example, suppose that f represents the velocity field of a fluid. Then del cross f of p is a vector that measures the tendency of a particle near p to rotate about the axis that points in the direction of the vector magnitude of the vector. The magnitude of del cross f measures how quickly that particle rotates around the axis. In other words, the curl at a point is a measure of the vector field's spin at this point. Now again, we will study the interpretation of the curl in greater detail in the last video of this series, where we look at Stokes' theorem. Alright, so we want to find the curl of this vector field here, x squared z, e to the y plus xz, xyz. So del cross f. Now again, we can think of this as a standard cross product. And remember, when we study cross products, we can set up a 3x3 matrix to evaluate it. So first row, the second row rather, will be partial x, partial y, partial z, and then we'll have x squared z, e to the y plus xz, and then xyz. And again, we can think of this as standard multiplication. So we'll get partial y of xyz minus partial z of e to the y plus xz. The second component flips the order, so we'll get partial z of x squared z minus partial x of xyz. And the final component, partial x of e to the y xz minus partial y of x squared. And if we look at this, right, partial y of xyz is xz minus partial z, that'll be x. We'll have x squared then minus yz as the second component. And in the final component, we have just z minus 0. And so there is our curl. And if we wanted to know the curl at point, we could just plug in the xyz values in here. So let's look at the relationship between the divergence and the curl. So consider a vector field F, which is given by PQR. Then del cross F, is del dot Ry minus Qz, Pz minus Rx, and then Qx minus Py, right? So this is the curl. Then if we take the divergence of this vector, notice Ryx minus Qxz, right? It's partial x here, partial y here, and then partial z here. Now, what we're going to do is just group all of our r's together. So we have Ryx minus Rxy. Group our p's together, we have Pzy minus Pyz. Group our q's together, we have Qxz minus Qzx. And remember that the order in which you take the partials doesn't matter. So no matter how you take the partials, no matter what order you take them in, it's the same thing. So this is 0, this is 0, this is 0. You get 0. So this is the relationship between divergence and curl. The divergence of the curl is 0. It will always be 0. We'll conclude this video looking at one of the more useful applications of the curl and the divergence. And in fact, it's very well known as Maxwell's equations. Anyone who has studied or is even familiar with electricity and magnetism knows of Maxwell's equations. These are a set of couple partial differential equations that form the foundation of classical electromagnetism, classical optics, and electric circuits. They describe how electric and magnetic fields are generated by charges, currents, and changes of the fields. Right? And here they are. You have Gauss's law, which is del dot E is rho over epsilon naught. We have Gauss's law for magnetism, which is del dot B is equal to 0. You have Faraday's law of induction, which says that del cross E is negative partial B partial T. And then you have Ampere's circuital law, which is del cross B is mu naught times J plus naught times epsilon naught times partial E partial T. And here, E is the electric field, B is the magnetic field, J is the electric current density, rho is the electric charge density, epsilon naught is the permittivity of free space. This is a fixed constant. And mu naught is the permeability of free space, which again is a fixed universal constant. So that concludes our initial look at vector fields.